I'm Hugo. I'm from the north of Portugal, Porto actually, and I work at INEGI. INEGI is an institute that works very closely to the Faculty of Engineering. We try to join the world of the academic research and the world of industry. And through that, although we do a lot of research work, we also do a lot of innovative work. And that's one of those projects that I'll be presenting here. So the wind energy, it's all around us. We all have heard of it. And nowadays, 20% of energy consumption in Europe is produced with wind power. And EU Commission believes that by 2050, this value will reach the 50%. This value has already been reached by Denmark nowadays, but there's a big problem with this. It's an effort that's been done by a long time, and our wind farms are getting to the end of the service life. So as we have these ginormous structures of reaching heights of 100 meters and blades with over 60 meters on length, assessing the structural integrity is of the utmost importance. Nowadays, although there are service maintenance plans for the big mechanical parts, the blades in itself, most of the times, are only assessed by the park workers visually. So we wanted to try to get a method that would be better than visually seeing it from the ground, that was fulfilled, that allowed us to inspect the entirety of the blade, and less expensive and more safe. So we wanted to have more clues than this visual spectrum, we went with Thermographic. So we use infrared cameras to get the infrared emissions that everybody produces, and get more information from what's behind the surface. So actually, this has already been done in literature, but only in small portions of all decommissioned blades, and never in the entirety of the blade, from what we have encountered with. So our methodology is acquire a thermographic image in the morning when the blade is cold, and then extracting another one when during noon with the full sun. So to get the hottest hottest time of the blade, and then convert them to temperature maps, post-process it, and by doing the differences, we can see the voids that possibly exist or exist in the blade as they heat up at different rates, and we'll have different values from the hottest part and the coldest parts. So first, we tried to recreate what was available in the literature in our laboratory setup, using these small parts of decommissioned blades, performing these small defects with 0.5 millimeters of depth, and by performing this subtraction, we didn't use the sunlight, we used a lightning system, and by performing this subtraction, we were able to see the defect quite clearly. These two defects were created through our experimental setup. We realized this by moving around the plate and seeing that they were not in the plate, but stationary in the setup. And also we can see that there is a possible delamination on this side. It's important to state that as we were already preparing for the real test and using UAVs or drones, we were already using a microbolometer, as the size of these thermographic cameras are much smaller. And these actually although it's not the same that we use in the real situation, the specifications are really close. So our first experimental test was performed at the north of Portugal in a wind park. And we used a 30 meters blade. And although we already were considering that these thermographic cameras have really low resolution, especially to the nowadays cameras type of resolutions, if we wanted to try to assess the entirety of the blade in one image acquisition, we would only get 6 centimeters per pixel, which is not actually a very good value. So we needed to get the drone closer and inspect bit by bit of the blade. For this, we used a Matrice drone. It's a very capable drone coupled with the commercially available Zenmuse and H20T camera, the T for Thermographic. This is a camera with a DJI microbolometer, very capable microbolometer, as well as the one on our laboratory. So these were the image acquired straight from the DJI camera. Here we see a 3-meter part of the blade, the tip part of the blade. We see an average temperature difference of 10 degrees. And this will be the part that I'm going to be presenting today, because it has the best results and it shows the method and how the methods work. So we can see from these photos that there is a disalignment on both of them. And as we want to do the subtraction, it was necessary to do some post-processing. First, by removing the background and only have the blade, then having the rotation of the noon image acquisition to fit the morning blade, and only then perform the temperature subtraction from one another. Here we also see the 10 degrees difference, but we have some other parts that reach the 20 degrees Celsius in this subtraction. As I stated, this is the 3-meter part of the tip, and although we can start to see some differences in other parts that could show some defects, we performed a square temperature difference that allowed us to much better visualize possible defects. So this blade is not a typical blade because it has an extension glued to it. So this blade was running for 15 years. At 5 years ago, it was inserted a 1.5 meters extension. It would be possible to say that the extension finished here and the old blade would finish over here. But that's not correct, because the extension needs to fit over the existing blade. And that's exactly what we see over here. Perhaps we see 3 areas on here. The first one, the top part, it's visually less impacted by time. And we believe that this is the extension part. Maybe this is an area of epoxy glue. This is the middle part that's actually the extension part and the older part of the blade. And here we see only the old part of the blade. We also see that the left side of the entire blade has much more damage than the right side. This is actually related to literature and to simple mechanical physics, because this is the leading edge, and the leading edge is the one that gets with wind, with raindrops, with dust, and so it gets much more damage than the other side. We also see some holes that are also visible in the visible spectral image, but we obviously see much more inference from much more information from this image than from this image. So we were capable of achieving a full field measurement, see beneath the surface of the blade and detect possible failures. Although we are not sure if these are or the severity, how severe they are. The big importance in this is that we can now, if further inspection is needed, be much more direct and assess much more clear or perform another test to the blade, which allows us to much better assess the structural integrity of the blade. So I would like to acknowledge this project as being funded by European Commission, Mariwind, and I also would like to invite you all to our next year's conference. It will be the 6th International Conference on Structural Integrity. It will be held on Madeira, Portugal. This is an island, and you're all invited. And I hope to see you next year over there. Thank you very much for your attention.